Hello AP Physics folks. Today I'm going to explain how to find the rotational inertia of a system of three masses that are located on the corners of an equilateral triangle. If I remember the problem correctly, we had an equilateral triangle. I'll sketch this out here like this, and we had three masses. Each of them, I believe, was 1 kilogram. So I'll label each one M. So that's M, and this is M, and this is M. And M is equal to 1 kilogram. And we're told that the length of each side of the triangle, L, was equal to 2 meters. And what we have to do is find the rotational inertia about the center of mass of this entire system. So I'm going to draw a little dot there at the center of mass. And let me pause for a second and shut my door. I've got some people coming. So we have the center of mass at the center of the triangle. And so the way we figure out the rotational inertia is for a discrete set of objects like what we've got, as opposed to a continuous mass, we take I equals 1 to 3 in this case. We've got three masses. And we take the mass I times the distance of that mass from the center about which we're computing the rotational inertia squared. And it's important to note here that the distance is going to be given by this line right here. So we'll call that distance A. Okay? And also notice, because this is an equilateral triangle, each of these A's is going to be the same. So I can write this as M1 A1 squared plus M2 A2 squared plus M3 A3 squared. And since all the masses are the same and all those values of A are the same, I can just write this as 3MA squared. So all we really need to do is figure out what A is right here. So in order to do that, that's A and L and A. We simply need to know how long A is compared to L. And to do that, we simply need to draw a little triangle in here. Maybe you remember this kind of thing. I'll probably have to work this out. It's an equilateral triangle, so this entire angle here is 60 degrees, so that the sum of the three is 180, which means that this angle right in here, I'll call that angle theta. Theta is going to have to be equal to 30 degrees. So this is going to be a 60-degree angle, a 30-degree angle, and a 90-degree angle. So we can figure out how big A is from this. I'll redraw this little triangle right here, where that is the length A. This is our center of mass, and that's our big mass right there. And this is our 30-degree angle right here. That side is going to be L over 2. So we know that cosine of that angle, cosine of 30 degrees, is going to be equal to the adjacent side, which is L over 2, divided by the hypotenuse. Remember, so katoa, so cosine is adjacent over hypotenuse, or in other words, A is going to be L over 2 cosine of theta, right? And that theta was 30 degrees. Well, what again is cosine of 30 degrees? Remember, if we have a 30, 60, 90 triangle, the sides have a ratio of 1 to 2 to root 3 for a 30-degree angle right here. So cosine of 30 degrees is going to be equal to root 3 over 2. That is the adjacent side length, root 3 over 2. So we know that A has to be equal to L over 2 times root 3 over 2, which is the same thing. Those 2's cancel out. It's going to be L over root 3. That's the length of A, the distance from the mass to the center of gravity of the system. Therefore, we know that the rotational inertia is equal to 3 times 1 kilogram times A squared. Well, A was 2 meters, and 2 meters over root 3, and we'll square this because it's A squared. So we'll have 2 squared is 4, over root 3 squared is 3. So we end up getting 4 kilogram meter squared. And so the rotational inertia of our triangle should be 4 kilograms meters squared. And that is the solution to this problem.